Hey guys, welcome to Pre-Calc lesson 8A.2, exponential functions. Let's start with a little warm-up here on our properties of exponents. Question number 1, 8 to the negative 5/3 power. So we've got two things going on here. We've got a negative exponent, which is going to take the reciprocal of our base, and then a fractional exponent. So just remember, the bottom number is the root, and the top is the power. So you might want to first rewrite this as 1 over the cube root of 8. We're going to take that to the 5th power. Cube root of 8 you should know is 2, and 2 to the 5th is 32. You can use your fingers to multiply that out, but that is one of our power families we should know. Question number 2, a lot going on here. Remember from yesterday's lesson, the first thing I like to do is take care of these negative exponents. So in an expression like this, I would just move those to the opposite, numerator or denominator, and take a second to write that out. All right, so this would go down here as t cubed. R to the negative 4 goes to the denominator as r to the 4th. R to the negative 7th goes to the numerator as r to the 7th. So now what I'll do is I'll take some time to simplify everything up top. So I've got 4 times the negative 6, that would give me negative 24. I've got r squared times r to the 7th, so that'd be r to the 9th. S to the 5th times s squared, so that's s to the 7th, and then I have a t. My denominator, I've got 3, so that's my coefficient. S, well, let me do alphabetical order, r to the 4th, s, and then t to the 8th. Okay, so now I just have to simplify that. Negative 24 divided by 3 is negative 8. If you notice here, I've got r to the 9th in the numerator, r to the 4th in the denominator. So I'd have an r to the 5th in the numerator. S to the 7th over s would be s to the 6th in the numerator. And I have a t over t to the 8th, so I'd have t to the 7th in the denominator. So there's my simplified expression. Moving on, number 3 looks worse than it actually is. Remember, when we're dividing, we subtract exponents. And if you notice, my denominators are the same, so it's really not that bad. I like to write stuff out. So this is going to be a to the 5/3 minus 8/3 exponent. And then I have b to the negative 1/4 minus negative 3/4. So if you can visualize that, that's awesome. I end up here with a to the negative 3/3, b to the 2/4. Now, to write this without a negative exponent, negative 3/3 is obviously a negative 1. That would go to the denominator as a, or a to the 1st, if you will. And then remember, 2/4 is the same as 1/2, which is the square root. So it just depends on what the directions say. Sometimes they'll say in simplest radical form, in which case this is it. If they say exponential form, you would just simplify this to a negative 1 and leave this as a 1/2. And then that would be good. There's your exponential form. Here's your radical form. Example 4 is a little bit challenging. If you notice the parentheses here, that indicates multiplication. So we're going to distribute 4mn to the negative 2 to both of these terms. And when you multiply your bases, we add our exponents. All right, so let's start. 4 times negative 2 is negative 8. M times m to the 5th is m to the 6th. N to the negative 2 times n cubed, you would just add those, so negative 2 plus 3 is just 1. Plus. Now you have a couple options here. Some of you might prefer to leave this as a fraction. Others might prefer to turn these into negative exponents and then add them. I don't care. I think it might be easier to visualize just this expression here, 4mn to the negative 2 over 2mn squared. So what I'll do in this expression is bring this down here. All right, so let me choose a different color so that'll cancel, and that'll be an n squared down here. Now if you wanted to simplify, we would have negative 8m to the 6th n plus 2 goes into 4 twice, so I have a 2. The m's cancel, and then I have n squared times n squared, so n to the 4th. So this is fine. you can leave it like this. If it said maybe no fractions, you might want to write it as negative 8m to the 6n plus 2n to the negative 4. Same thing. Okay, what we're going to be doing today is graphing exponential functions without the use of a calculator. An exponential function involves the expression b to the x, where the base b is a positive number. So that's also important, positive number other than 1, because that'd be kind of pointless if our base was 1. So what I'm going to do very quickly here, if we start with f of x equals 2 to the x, let's think of all our powers of 2, and I want over this interval of negative 3 to 3. So let's start here, negative 3, negative 2, negative 1, 0, 1, 2, 3. So remember what the negative exponent does. It takes the reciprocal of our base. So 2 to the negative 3 power is 1 over 2 cubed, or 1/8. 2 to the negative 2 is 1 over 4. 2 to the negative 1 is 1 over 2. Anything to the 0 power is 1. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. So if we plot those points, obviously I have to sort of estimate in here, but negative 3, 1/8 would be really close to that x-axis. Then you have 1/4, then 1/2, then 0, 1, 1, 2, 2, 4, and 3, 8. Now, if we're just graphing over that interval, I would just connect those in this nice curve, like so. But in reality, we should recognize that this would continue upward, and this continues towards the x-axis without touching it. All right, so spoiler alert, this x-axis is a horizontal asymptote. All right, so what are our intercepts? Well, the intercept is right here. It looks like there's only one, 0, 1, so y-intercept. The domain would be x is an element of all the reals, because like we said, it really continues that way forever and continues that way forever. The range, since we said this is an asymptote, the range is going to be y is greater than 0. Now, we're going to talk about key points when it comes to exponential functions and graphing. The two key points are going to be these two right here, 0, 1, and 1 base. And that's how I want you to remember. 0, 1 is on every exponential graph that does not have a transformation. Because if you think about it, any base to the 0 power is 1. The other key point that will be on every exponential function is 1 comma base. Because any base to the first power is itself. So these two right here will be on every exponential function, and this one is going to be the same as the base. All right, so take a look at this graph, and let's answer this question. What happens as x approaches negative infinity? So as the graph goes this way, that's when x approaches negative infinity. What's happening to your graph? Well, it looks like it's getting closer and closer to the x-axis. So we'll say something like y approaches 0, because the y value is getting closer and closer and closer to 0, but it'll never get there. So we say approaches 0. What happens as x approaches positive infinity? So as x approaches positive infinity, means we're moving to the right. Well, what's happening as we move to the right? Well, it keeps going up and up and up and up. We say y approaches positive infinity, or just infinity. All right, let's compare different bases. And again, I'm going to go through this pretty quickly. Graph y equals 3 to the x. So from what we just mentioned, we said key points are going to be 0, 1, and 1 base. So in that case, it's going to be 1, 3. So 0, 1, 1, 3, and negative 1 is going to be 1/3. So I'll just put that in there real quick. To make this really accurate, it would be also 2, 9. So let's see if I can fit that on here. 3, 3, I can. So it'd go through that point as well. So there's the function y equals 3 to the x. How about y equals 7 to the x? The key points would be 0, 1, and 1, 7. So it also go through this point, but then it'd be 1, 7, 4, 5, 6, that's here. So I think it's obvious on this side of the y-axis that the graph is steeper. But here's what's interesting. Think about 7 to the negative 1 is 1/7. It would actually dip down below the other graph here. So the bigger the base, the quicker it grows vertically, and the quicker it moves towards the horizontal asymptote. It just makes it more extreme in both directions. Okay, quick review here. Components of an exponential function. The y-intercept we talked about will always be 0, 1, unless we transform it, which we'll do in a few minutes. There's always a horizontal asymptote at y equals 0, which remember is simply the x-axis. And rapid growth as x approaches infinity. All right, so let's try a few examples here with transformations. So from earlier in the year, we have to recognize what each one of these numbers does to my parent function. So an x minus 3 moves it to the right 3, and a plus 1 tacked on the end is up 1. So here's how we're going to handle this situation. We are going to shift our axes right 3, and up 1. So I want you to visualize this now as our new origin. And remember, we have key points. My base is 2, so without these transformations, my key points would be 0, 1, and 1, 2. So even though those aren't the actual coordinates on the graph, those would be the coordinates from this point. So from here, pretend this is the origin, 0, 1, and 1, 2. So it's going to go through these two. Here's my asymptote, and it grows rapidly in this direction. All right, so let's plot those points. This is our pretend 0, 1. Then we have 1, 2. Because 2 is kind of a small base, if my input is 2, my output would be 4. So just for the sake of sketching, that would be good there. And you'll be asked to identify 3 points on the graph. So now, what are the actual coordinates of these 3 points? Okay, so those actual coordinates would be 1, 2, 3, 2, 4, 3, and 5, 2, 5, 5. Now, when you're done, this is calculator inactive. How do you know if you sketched it correctly? Well, what we're going to do is we're going to take these, plug this in for x, plug that into y, here, see what we get. So let's try the x first. 2 to the 3 minus 3 plus 1. Well, this is 0. 2 to the 0 is 1. 1 plus 1 equals 2. That's my y value. That one worked. Let's plug in a 4. Okay, so 2 to the 4 minus 3 plus 1. That's 1. 2 to the first is 2. 2 plus 1 is 3. That's my y value. Now let's try 5. Plug a 5 in. 2 to the 5 minus 3 plus 1. Well, that's 2. 2 squared is 4. 4 plus 1 is 5. Got it. So I know that this is the correct sketch. Whoa. All right, so what do we have here? Let's review our reflections. Okay, so I have this graph sketched here, y equals 4 to the x, 0, 1, 1, 4. If you remember, this negative here, if it's on the outside, the first thing you see is a reflection in the x-axis. So if I were to reflect this graph in the x-axis, this point here, 0, 1, would become 0, negative 1, and 1, 4 becomes 1, negative 4. So quickly sketching that in, I have this. So there is y equals negative 4 to the x. Okay, if our negative is inside the function, okay, that is a reflection in the y-axis. So now if I take a picture of or a reflection of the white graph in the y-axis, 0, 1 stays there, 1, 4 becomes negative 1, 4. So that graph kind of looks like this. So that's y equals 4 to the negative x. And our last one, we'll check that out, it does both. So that's a reflection in the x-axis and a reflection in the y-axis. So basically what we can do is you can take the blue one and reflect it in the y, you can take the red one and reflect it in the x, but it's going to look like this. What's nice about an exponential graph, I'm sure you guys don't think it's nice, but every reflection looks different. You know, like with a parabola, really only one reflection looks different. So that would be y equals negative 4 to the negative x. All right, let's move on. What happens when our base is less than 1? So y equals 3 to the x. Key points there would be 0, 1, and 1, 3, right? 0, 1, and 1 base. No problem. I can sketch that. It would also be 2, 9, so I have room to put that one in there because 3 squared is 9. So there's y equals 3 to the x. What happens if your base is less than 1? This concept still applies. 0, 1, 1 base. Well, in this case, our base is 1/3. So let's see what happens. 0, 1, 1 base. 0, 1, 1, 1/3. Huh. So it appears, and I bet if I put in a negative 1, you take the reciprocal, that becomes 3, that this is a reflection. And it'd be negative 2, 9. So this is the equation y equals 1/3 to the x. Why is that? Well, let's think about this. 1/3 equals 3 to the negative 1. So it turns out this here is the same as this reflected in the y-axis. It should totally make sense. So now we can generalize that. General shape of exponential functions. If your base is greater than 1, that's our traditional exponential, looks like that. Think of exponential growth. If your base is less than 1, it'll look like this. Because when you take 1/2 and you multiply it by 1/2, it gets smaller. So if our base is less than 1, every time you multiply it by itself, it keeps getting smaller and smaller and smaller. That's why you have this general shape. All right, let's try a couple with vertical stretch. All right, so y equals 3 to the x. So it's 0, 1. Let me write these down. I should be writing these down. I'm going a little too fast. 0, 1, and 1 base. Okay, 0, 1, 1, 3. It would also be 2, 9. I can fit it in there, so I'll sketch it. All right, well, what happens if I take 2 times 3 to the x? Well, what we are doing is we are taking our output, our y, and we're multiplying those by 2. So instead of 0, 1, it's 0, 2. Instead of 1, 3, it's 1, 6. Okay, so 0, 2, 1, 6. Obviously, I don't have room for the other one, but it's going to look like this. Every y value is twice the other graph's y value. And there's y equals 2 times 3 to the x. So what transformation took place? This is a vertical stretch times 2. Now, there's a real easy way we can apply this to our sketches, writing the equations of exponential functions. Y equals a times b to the x. So in this particular graph, if my base is 2 and my y-intercept is 5, look at what happens. 1, 2, 3, 4, 5 has to go through that point. That is the point 0, 5. Now, because one of my key points is 0, 1, that's 1 on the y-axis, any vertical stretch is just going to be this number, the y-intercept, because it's going to be 1 times what is this? Well, that's always this number. So what's nice about this is that A must be 5 in this case. If I know that my base is 2, my equation has to be then y equals 5 times 2 to the x. So what's going to happen in the next group of examples is we are going to give you either 2 points, a base and an intercept and a point, and you're going to write the exponential equation. And this is the part that's a little bit new in this course. The rest is theoretically a review from Algebra 2. So let's crank out a bunch of these. It really goes quick. It's the same process over and over again. I'm going to do 5 or 6 of these, maybe just 5, and I think you'll get the hang of it in the next few minutes. All right, so I want you to write the equation of this exponential function. I know the equation has to look something like this. Y equals AB to the x. And what we are going to do is we are going to replace the A with the vertical stretch and the B with the base. And they'll give us all sorts of information. So, first example, it says the y-intercept is 6. Well, what we just said is that y-intercept is always the vertical stretch. So if they tell me the y-intercept is 6, guess what? A is 6. So I could replace this with a 6. Now, they didn't tell me what the base was, right? They're not all going to be that easy. So what they're telling me here is that f of 1 equals 18. This is just another way of saying, oh, the point 118 is on this function. Or that x equals 1 and y equals 18. So what we're going to do to get the value of b is we have to solve this equation. We're going to put a 6 in for the a. We're going to put a 1 in for the x. And we're going to put an 18 in for the y. All right, so let's see how that works. Y we said was 18. A we said was 6. We don't know b, we're solving for it. X is 1. Well, that's pretty easy. Divide by 6, b equals 3, right? B of the first is b. So now I can write that equation. Y equals a, which is 6, times your base, which is 3, to the x. Okay, let's keep plugging away at these. You're going to notice the same pattern over and over again. We're just going to change up the numbers. This right here, f of 0 equals 3, is another way of saying, oh, the point 0, 3 is on this exponential function. Well, 0, 3 is simply the y-intercept. So when they give you this, a is 3. Remember, I don't always write this out, but we're plugging into this. Y equals ab to the x. This tells me x is 2, y is 48, and I know a is 3. So I'll plug these in here, here, and here, and we solve for b. All right, so y, 48, equals a, 3, times b, what's x, 2. Well, this one's only moderately more difficult because I'm going to have to take a root at the end, a square root. So first thing I'll do is divide by 3. 48 divided by 3 is 16. That's b squared, square root, b equals 4. So once you have that, and you know a, we can write our equation. Y equals 3 times 4 to the x. Now this is all calculator inactive, but as you're doing your homework, you could obviously throw this into your calculator very quickly to see if when you plug in a 2 for the x, do you get 48? Right? You actually don't need a calculator. 4 squared, 16. 3 times 16, 48. So I know that works. Okay, numbers moderately more difficult here. What we talked about, f of 0, that's the point 0, 1/10. So here, a equals 1/10. Remember, this is your x, and that's your y. So I'll plug into that general equation. I'll have y, which is 12.5, equals a, which is 1/10, times b, which I don't know, to the x, which is 3. So you're like, wow, this is kind of a mess, but not really. All we're going to do is multiply both sides by 10 to get rid of this fraction. And that gives me 125 equals b cubed. You should be able to do this without a calculator. The cube root of 125 is 5. There's your value of b. There's your value of a. So this equation is y equals 1/10 times 5 to the x. Might be a little bit more challenging here. Let's see. Plug in a 3. So 5 cubed is 125. That's not too bad. 125 divided by 10, 12.5. Got it. Okay, last two. We'll finally wrap this up. Y-intercept is -2. Okay, what does that tell me? A is -2. X is 3. Y is -1/32. So let's plug into that general equation. The y value, -1/32, equals a, -2, times our base, which we're solving for, to the x. So now this one, I need to divide by a -2. Okay, well, dividing by -2 is the same thing as multiplying by -1/2, right? I don't really want to divide fractions, so let's think of multiplying by the reciprocal. Well, those will cancel, and that gives me b cubed. -1/2 times -1/32 is 1/64. Well, now I take the cube root, and yeah, it's a fraction, but it's really not that bad. You should know the cube root of 64 is 4. This gives me 1/4, and there's my b value. There's my a value. Here's your equation. Y equals -2 times 1/4 to the x. And again, you can check this pretty easily. Plug in a 3 here. 1/4 cubed is 1/64, and 2 times that is -2/64, or -1/32, and that one works as well. Okay, last one here. Number's just a little bit bigger. We've already talked about it. They're telling you the base is 3. Oh no, so this one is a little bit different. My base is 3, so that's b. They're not giving me a here. X is this, y is that. So let's plug into the equation. Y equals, so 5 equals a, I don't know it, so I'll leave it a, times b, which is 3, to the x, which is 4. So basically what I have to do here is I have to divide both sides by 3 to the 4th. Again, this would be calculator inactive. We should know our power families. 3 to the 4th is 81, so a is 5/81. We would obviously leave it as a fraction. So now I know my a value, I know my b value, and I can write this equation. Y equals a, 5/81, times b, 3 to the x. All right, that finally concludes Day 2, Unit 8A. As usual, guys, if you have any questions, please don't hesitate to reach out. Thanks a lot for watching, and we'll see you in class soon.